Welcome to The Explainer. Today, we are diving headfirst into one of the most profound and, let's be honest, one of the most puzzling concepts in all of science. We're talking about quantum entanglement, a mystery that really forced us to question the very fabric of reality itself.
All right, so to really get our heads around this, we're going to follow a clear roadmap. We'll trace the whole story, starting from the predictable, comfortable world we thought we knew, all the way to the strange, deeply interconnected reality we've discovered.
So, our journey kicks off right around the turn of the 20th century. You see, for hundreds of years, physics felt solid, predictable, almost solved, you could say. But as scientists started to probe the tiny realm of atoms, those solid foundations, they just began to crumble, and I mean spectacularly.
For centuries, we have this really comforting idea from Newton, this clockwork universe. You give me the starting conditions of an object, and I can tell you its entire future with perfect accuracy. Simple, right? But down at the atomic scale, those ironclad predictions completely failed. The new paradigm, quantum mechanics, said something just wild. It said the best you can do is calculate probabilities. It turns out reality plays dice.
You know, the failure of those old rules, it didn't just leave a vacuum. It opened the door to a whole new way of looking at reality. This probabilistic nature of the quantum world. It introduces this fundamental layer of weirdness that changes basically everything we thought we knew about how things work.
And right at the heart of this new reality is a concept called superposition. What it means is, before you actually look at a particle, it doesn't have a definite state. It exists in all of its possible states simultaneously. Imagine an electron spin. It's not up or down. It's this kind of weird, ghostly blend of both up and down at the exact same time.
So you might be asking, how do we get from that fuzzy, all-at-once state to the solid, definite world that you and I experience every day? Well, it all comes down to the act of measurement. The very moment we observe that particle, its wave of possibilities just collapses. It snaps into a single concrete outcome. It's almost as if the universe is holding its breath, existing in this haze of pure potential, until we look and force it to make a choice.
Now, this probabilistic world was already strange enough to wrap your head around. But there was another property of quantum mechanics, one that grew out of this idea of shared states, that would ignite one of the greatest and most important debates in the entire history of science.
Albert Einstein himself found one particular implication of the theory so utterly absurd, so contrary to all common sense, that he gave it this famous and pretty dismissive nickname. He was absolutely convinced that if this spooky action was real, it could only mean one thing: the whole theory of quantum mechanics had to be incomplete.
What he was talking about was quantum entanglement. This is a state where two particles can become so deeply interconnected that, for all intents and purposes, they're no longer separate things. They're described by a single, shared quantum state, a single mathematical blueprint for both of them at once. They effectively act as one object, even if they're on opposite sides of the galaxy.
And this right here was the core of the famous EPR paradox. Einstein's argument was just plain common sense. He said, look, if I measure the spin of one entangled particle and find out it's up, I instantly know its partner must be down. To him, there's no way that was a random outcome decided at the moment of measurement. The only logical way to explain it was that the particles carried some kind of secret instructions, what he called hidden variables, from the moment they were created. Otherwise, you'd need some kind of faster-than-light communication, and that breaks a fundamental rule of the universe. And that argument, that paradox, set the stage for a truly monumental clash of ideas between two titans of physics. And this wasn't just some academic squabble over formulas. This was a battle for the very nature of reality itself.
So on one side you had Einstein. He was championing what we now call local realism. Basically, things have definite properties whether we're looking or not, and nothing can travel faster than light, period. But on the other side, you had Niels Bohr, who argued that it's actually meaningless to even talk about a particle's properties before you measure them. That fuzzy quantum state, it isn't incomplete, it is the complete description of reality.
For decades, this was pretty much a philosophical standoff. I mean, how could you possibly test what reality's doing when you're not looking at it? It seemed impossible. Then, in 1964, a physicist named John Bell had an absolute stroke of genius. He devised the theorem that could actually put reality on trial. He turned this philosophical debate into a real, testable, experimental question. Bell's incredible insight was to turn this whole thing into a numbers game. He proved, mathematically, that if Einstein's hidden variables were real, there would be a very strict limit on how strongly the measurements on two entangled particles could be correlated. But quantum mechanics? It predicted correlations that would go way beyond that limit. Suddenly, the two worldviews made different, testable predictions.
And so, when physicists like Alain Aspect and John Clauser finally managed to run the experiments, the results were, well, they were unambiguous, stunning, and they changed everything. The universe violates Bell's inequalities. The predictions of quantum mechanics were right all along. Einstein's cherished common-sense idea of a local, realistic universe was wrong. The world really is spooky.
But here's the thing. This isn't just some abstract philosophical point scored in a textbook. This deep, strange, non-local connection that Einstein hated, it's the engine behind a whole new generation of technologies that are being built as we speak.
You can see the applications popping up everywhere. Entanglement is what allows quantum computers to perform calculations that would take the best supercomputers we have today literally centuries to solve. It's the foundation for quantum cryptography, creating encryption so secure that any attempt to eavesdrop would instantly be detected because it would disturb the entangled state. We're talking about building a quantum internet where security is guaranteed by the laws of physics, not just by complex math.
So, at the end of the day, we've been forced to accept a universe that is profoundly interconnected, where particles aren't just isolated actors, but are fundamentally parts of a single, unified system. We've learned that our common-sense ideas about how the world works, locality, and realism, they just don't apply at the deepest level. Which really leaves us to wonder, if reality is built on these strange connections, what other fundamental secrets does the quantum world still hold?